Hey guys, so some quick and dirty ways to talk about or to think about how you know when you've got increasing entropy or increasing dispersion. So think about this. Increasing dispersion means delta S is positive. So start with kind of an easy idea first. If you think of phases, solids, liquids, and gas. And just think about how you have particles. You got dots. All right, guys, I'm going to tell you, during this COVID crisis, my artwork has not gotten any better. So a solid is very ordered. It's regulated. It's a regular pattern. Things are compact. Your particles are not dispersed. Liquid. It's always your hybrid between the two, between gases and solids. So you've got a container. And if you would describe a liquid, the particles have motion. It's not vibrational, they can move, but they kind of flop and rotate over each other. So they have somewhat free movement, but they're still packed in kind of tight. So you're going to be something like, I got 15 of those. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You've got more space between the particles, but you still can't, you can't really compress a liquid, not very well. Versus a gas, I'm going to draw an extra big container here to exaggerate. So I'm showing those same 15 particles. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Things are definitely more spaced out. Your energy is more dispersed, and that makes sense if you're talking about temperatures. If you're keeping things at roughly the same pressure, solids exist at a lower temperature. Your particles have a lower kinetic energy. Liquids have a higher temperature. They're at a slightly higher kinetic energy. And gases, you've got more molecular motion. They're all over the place. More dispersion, less dispersion, least. Makes sense. Gases are going to have higher entropy, liquids lower, solids the least. Pretty easy. Okay. The other easy thing to think about is, what about if you just have more moles, more particles? So if you take a big molecule and you just blow it to smithereens into a bunch of smaller pieces, that's going to be more dispersion. So you think about, burning glucose or burning a fuel. I can do this generically, and then I'll give you an example. Generically, it looks like this. You look at this reaction here, and we don't know what C and D are, we don't know what A and B are, we don't even really know what phase they're in. It almost doesn't matter. You've got 2 moles of particles on your reactant side, and you've got 5 moles on the products. So you've created more particles in this process. You've got more entropy being produced. You've got more energy dispersion. because you've got more pieces that have been produced. Entropy has increased. You've created more disorder. If you want to see this in something that I've used a lot, if you look at the reverse of the Haber process, two moles of ammonia breaking down into 1 mole of nitrogen and 3 moles of hydrogen gas, 2 moles turning into 4 moles. Dispersion has increased. Disorder has increased. Entropy has increased. These other ones then, based off of that, hopefully make a little bit more sense then. So if you take a solid, trouble here. So here's your container. Here's your solid. That's your container. There's some water in there. And as the solid dissolves and little pieces break off, so that maybe you lose a little bit of your solid, what happens to your entropy? Now let me make these dots a little bit bigger as I'm looking at my own camera here. It's like, ew, that looks like nothing on the screen. That's much better. So as you dissolve a solid, you increase entropy because you're taking away part of something that was very much ordered, and you're now destroying that order. You're putting space between those particles. You're making it hard for them to get back together. Oh, well, if you mix two liquids, and in your reading it says dissolve a liquid, imagine if you took, you know, a little bit of acetone and dissolved it in a lot of water, or you took a little bit of rubbing alcohol and you dissolved it in a whole lot of water. It's the same thing. You're increasing entropy. You're keeping those particles from each other. I wanted to, and I'm trying to save beverages for, you know, while we're in this crisis in case we run out. The same thing happens when you open a can of soda. And if you've got dissolved gas, so here's my can of RC Cola. Not an artist. Shut up, everybody. So here's the tab. And when that opens, what happens? Your carbonation, CO2 leaves the solution. So all this fizz starts to come out. So you have gas that's been forced into that solution. You give it a way out, it wants out. So when dissolved gas escapes, guess what? Entropy increases too. Same thing when you evaporate a gas. It's going from a liquid phase to a gas phase. All of these things increase disorder. In fact, I'll put it in my next video a little bit here to make it start. You want to make sure you understand phase transitions, because when a substance gets heated, that process is endothermic. It's a positive delta H. It's absorbing energy. But it's actually increasing disorder because those particles are getting excited and they're moving. And then when it goes from solid to liquid, oh, well, those particles are now actually further apart. So it's a positive delta H It's sucking up heat, but it's also increasing disorder. And when the substance cools down, it's releasing heat, which is exothermic, but it's increasing order because it's allowing those particles to get closer together and eventually do a phase transition. It's interesting to think about. Stop there, pick that back up.